Hi and welcome to this video on group theory. This video is primarily aimed at students revising for their A-level maths and or further maths exam, as well as students preparing for or partaking in a STEM-based degree. If this is the first video from my collection that you are watching, you may want to take some time to watch my introductory video. This should give you a better idea of how to get the most out of these videos. So let's start off with some background. The members of a set are often called its elements. Sets also have something called a binary operation. This is usually denoted with a little circle like so. A binary operation on a set S is a rule. It assigns to each ordered pair of elements, say x of y in S, exactly one element denoted by x circle y. The binary operation x dot y here does not have to be an element of the set S. If the binary operation on S always gives a result which is in the set S, then the operation is said to be closed within the set, but more on that later. So let's move on to some terminology. First of all, let's look at commutativity. A binary operation on a set S is commutative if A dot B equals B dot A for all A and B in the set. And I'm going to call the set S. This means that if the binary operation applied to A and B is the same as the binary operation applied to B and A for all A and B in S, then it is commutative. For example, addition is generally commutative, as, say, 2 plus 3 equals 3 plus 2. If this does not hold true, then it's not commutative. Next, let's look at associativity. A binary operation on a set S is associative if the binary operation applied to A and B and then applied to C is the same as the binary operation applied to B and C and then A and B and C. And this needs to hold true for all A, B and C in S. If this does not hold true, then the set S is not associative. Next, let's look at what an identity element is. If S is a set with a closed binary operation, if there exists an element E, which is in the set, such that for all A in the set, if you apply the binary operation between E and A, it equals A with the binary operation applied between A and E, which just equals A. If this is the case for all A in S, then E is the identity element. Now let's look at an inverse element. If a set S has a closed binary operation, then for each element A, in the set S. If there exists an element B, in the set S, such that you can apply the binary operation between B and A, and that's going to equal the binary operation applied to A and B, which is going to equal the identity element E. Then B is known as the inverse. How does that terminology help us? Well, a set G with binary operation again expressed by this little circle is called a group if it has the following four properties. 1. It is closed. This means that if you apply the binary operation to any elements in the set G, then the result will also be in G. So A with the binary operation applied to B is in G for all A and B in G. Associativity. The set must be associative, so as before, A dot B dot C has to equal A dot B dot C for all A, B and C in G. And that's what this notation here symbolises for all. There must be an identity element, which I'll call E. So as above, we need an identity element E such that A dot E equals E dot A, which equals A. And finally, there must be inverse elements. So as above, this means that for every A in G, there must be a B in G, such that B dot A equals A dot B, which equals the identity element E. The number of elements in a group is called its order. So if a group has an infinite number of elements, it is said to have infinite order. Also, if a group has a binary operation, which is commutative, then this makes the group an abelian group. If H is a subset of G, and they share the binary operation, then this implies that H is a subgroup of G. So a subgroup is just a group that is part of a group. And every group has two trivial subgroups. This is the group with just the identity element En and the group itself. All the other subgroups of G that are not the identity element or the group itself are called proper subgroups. The order of a subgroup of a finite group divides the order of G. So the order of H divides the order of G if G is finite. A group of prime order has no proper subgroups. Let A be an element of a group G. Then A is said to have finite order if A to the power of n equals E, the identity element, for some positive integer n. The least such n, such that A to the power of n equals E, the identity element, is called the order of A. If no such n exists, the element A has infinite order. The order of an element of a finite group G divides the order of the group G. Let G be a group. If there is an element A in G, such that every element of G has the form A to the power of n, for n which is an integer, then G is called a cyclic group. The element A is called a generator for G, and the notation G equals A in this way is used to show that G is generated by A. And finally, moving on to see what it means to be an isomorphic group. Isomorphic means equal in form. So when the word is applied to a pair of groups, it means that the groups are structurally the same as each other. So if we have two groups, G and H, they are isomorphic if there exists a function f which maps between the two groups such that the range of f is in H, f is a one-to-one function, and f of a dot b equals f of a dot f of b for all a and b in the group G. If these all hold true, then the function f which maps from G to H is an isomorphism. If we have an isomorphism, then firstly, if E is the identity in G, then f of E is the identity in H. Secondly, if a to the minus 1 is the inverse of a in G, then f of a to the minus 1 is the inverse of f of a in H. And thirdly, the order of an element A in G is equal to the order of f of a in H. And all infinite cyclic groups are isomorphic. Thank you for listening to my video.